Deep within a granite mountain carved out of the earth near Colorado Springs, a monumental task reached its quiet culmination on April 20th, 1966. Construction crews meticulously bolted the last of 1,319 colossal steel springs into place. These springs, each a testament to industrial might, were destined to bear the immense weight of an entire complex. Three-story steel buildings, combined weighing thousands of tons. For those outside the project, the sheer scale of this endeavor and its baffling purpose remained a profound mystery. Why would a structure already ensconced within a chamber blasted half a kilometer deep into solid rock require such an elaborate, spring-loaded foundation? It defied conventional logic. Yet, engineers had dedicated years, investing tens of millions of dollars to ensure this subterranean city could, quite literally, bounce. The underlying rationale was both stark and terrifying. In the chilling calculus of the Cold War, the threat of a Soviet nuclear strike against the United States military command network was not merely theoretical. Should such an attack materialize, the immense shockwave propagating through solid granite possessed the destructive power to obliterate any rigidly mounted structure with the same effortless ease as a dropped ceramic plate shattering on concrete. The solution, born of desperation and genius, was counterintuitive. Instead of attempting to defy the shockwave's raw power, engineers conceived a design that would yield to it. The entire command center was engineered to float, suspended on a vast subterranean forest of giant steel springs. This intricate system allowed the massive buildings to sway, absorbing the cataclysmic energy, ensuring continued operation even as the mountain itself absorbed the brunt of the blast. This is the story of Cheyenne Mountain, a fortress forged not just from rock, but from an audacious act of engineering foresight. It is the tale of a complex built to endure a direct nuclear strike and the strange, almost unbelievable trick that allowed an entire underground city to move. By the late 1950s, American military strategists confronted a dilemma far removed from the conventional concerns of missiles or bombers. Their problem was one of geography, of exposure. The North American Aerospace Defense Command, or NORAD, bore the critical responsibility of detecting and coordinating any response to an incoming Soviet assault, be it from bombers or intercontinental ballistic missiles. Yet, NORAD's initial command centers were housed in ordinary structures, vulnerable targets on conventional air bases. A single, precisely aimed strike could instantly blind and deafen the entire continent's early warning system, plunging it into chaos. This inherent fragility escalated into an existential alarm with the 1957 launch of Sputnik. The satellite's orbit served as undeniable proof. The Soviets now possessed rockets capable of delivering payloads anywhere on Earth. The terrifying implication was clear. If America's ability to detect an incoming attack could be destroyed, the very cornerstone of nuclear deterrence, the promise of devastating retaliation, would crumble. Planners urgently needed a command center engineered not just to survive, but to function through the immediate aftermath of a direct nuclear impact, coordinating a response when the world above might be tearing itself apart. The chosen solution, radical in its simplicity, bordered on the medieval. Bury the entire command structure deep within a mountain. Cheyenne Mountain, a 9,500-foot granite peak near Colorado Springs, emerged as the prime candidate. Its solid, ancient granite offered a natural shield, a bulwark against the unimaginable forces of the atomic age, promising to safeguard the beating heart of a nation's defense. Beneath the rugged surface, far from the sprawling lights of any city, a monumental undertaking began in 1961. The chosen site was not arbitrary. It was a deliberate selection, dictated by the Earth itself. Here, a colossal mass of dense, unyielding granite offered a natural, formidable shield, ideal for absorbing the raw, destructive energy of an atomic blast. Its very remoteness, a strategic isolation from major population centers, was part of its genius. For 5 relentless years, crews toiled in the Earth's embrace, their controlled detonations carving out an immense subterranean void. They removed a staggering volume of granite, enough to fill a stadium to its brim, creating a space where something utterly unprecedented would rise. Within this cavern, they constructed a complex of freestanding buildings, physically detached from the rock around them. These were not mere structures. They were meticulously engineered fortresses designed to survive a shockwave that could otherwise crush anything bolted directly to the mountain's stone walls. But the true test of human ingenuity lay not in the brute force of excavation. The real, terrifying challenge was yet to reveal itself. How to protect the structures within this hollowed-out mountain when the very earth around them began to convulse. Blasting a chamber into solid, sheer physical effort, it undeniably was. Crews employed precise, incremental blasting techniques, meticulously extracting roughly 693,000 tons of granite over several years. This monumental effort carved out a sprawling complex of interconnected chambers, vast enough to house 15 separate buildings, several of them soaring 3 stories tall. These internal bastions were linked by tunnels wide enough to accommodate the passage of heavy trucks, forming an intricate, self-contained world beneath the earth. Yet, rock removal, while immense in scale, was a known engineering discipline. Mining companies had been perfecting versions of this art for over a century. The genuinely unsolved problem, the one that haunted the engineers, was what happened after the rock was gone. How could a command center, fragile and brimming with delicate electronics, be shielded from a nuclear shockwave when it sat encased within solid stone? Here lies the profound, counterintuitive paradox. The common perception suggests that burrowing deep underground offers sanctuary from a nuclear strike. In terms of direct, immediate destruction from a surface blast, this holds true. Yet, the Earth itself harbors a treacherous secret. A nuclear detonation, even 1 mile away, unleashes a colossal compression wave that rips through solid rock with terrifying efficiency. This shockwave travels through granite far more effectively than it propagates through air. Imagine a structure bolted rigidly to that granite. It would not be shielded. It would become a direct conduit for destruction. The shockwave would transmit through the stone faster and with far greater force than through air, slamming into the anchored building with the instantaneous violence of a colossal hammer blow, shattering its very foundations. A building fixed immovably to the rock would not be protected by the mountain. It would be victimized by it, becoming an extension of the Earth's violent tremor. Engineers grappled with this fundamental dilemma. They needed a revolutionary method to mechanically disconnect the internal buildings from the mountain itself. The goal was audacious. Even if the colossal granite mass around the complex flexed and shuddered under a nearby strike, the intricate structures within would barely register the impact. This meant the entire complex needed to float, isolated within its granite shell. It was a concept closer to a suspension system than a mere foundation, an architectural audacity never before conceived, let alone constructed, at this monumental scale for this singular, critical purpose, anywhere across the globe. The true intellectual leap occurred when brilliant minds ceased to envision buildings as static masses anchored to solid earth. Instead, they began to design them as vessels, engineered to float, not upon water, but on an unseen ocean of meticulously crafted steel. The solution, a testament to human ingenuity under extreme pressure, manifested as a spring-mounted foundation system. To this day, it stands as one of the most ambitious base isolation projects ever realized for a military installation. A fortress within a mountain designed to defy the very ground it occupied. Rather than simply pouring concrete floors directly against the unyielding rock walls of the subterranean chamber, construction crews embarked on a far more complex endeavor. Their first step involved erecting a secondary steel understructure, an immense internal skeleton of girders and beams, a metallic armature within the cavernous space. Upon this intricate framework, the entire building, a colossal structure in its own right, was then meticulously mounted. The colossal weight of the facility would ultimately rest upon 1,319 custom-engineered coil springs. Each individual spring stood approximately 4 feet tall, a formidable cylinder of coiled metal weighing a staggering 1,000 pounds. These were not generic components plucked from an inventory shelf. Every single spring was a bespoke creation, precisely calibrated to bear a calculated fraction of the building's immense total mass. Yet critically, each was also designed to permit several inches of nuanced horizontal and vertical movement in any direction. Imagine, if you can, an enormous, vital complex, not rooted to the bedrock, but poised delicately, yet firmly, upon thousands of individually calibrated shock absorbers. These colossal springs were distributed with an almost surgical precision, ensuring that no single component bore a disproportionate load. This intricate ballet of engineering allowed the entire structure to sway, to breathe, as one cohesive, connected unit. It was a design imperative. The building had to move in unison, preventing any uneven twisting or shearing forces that could rip it apart from within. The mathematical equations underpinning this design were relentlessly unforgiving. Every single spring had to be matched with absolute precision to the building's intricate weight distribution. This meant accounting for thighs. The goal was a seamless, synchronized response. The entire structure had to rise, tilt, and settle evenly, without any sudden violent lurching at odd angles. Such uncontrolled movements could catastrophically snap vital pipes, misher reinforced concrete walls, or wrench crucial equipment from its mounts. Engineers meticulously modeled the anticipated shockwave forces, drawing upon invaluable data gleaned from actual nuclear test detonations. They calculated the theoretical maximum displacement the ground could experience, then ensured that the spring system possessed more than enough travel distance to absorb that colossal motion. The paramount objective was unwavering. The building must never, under any circumstance, make rigid contact with the surrounding rock walls. Because the buildings were designed to move independently from the mountain's embrace, nothing could be rigidly connected across that critical protective gap. Water pipes, electrical power cables, and communication lines, every single conduit carrying lifeblood to the facility, had to traverse from the fixed rock walls into the floating buildings through specially engineered flexible couplings. These were, in essence, giant resilient joints designed to flex and stretch, maintaining vital connections even as the entire world around them shuddered. Deep within the colossal granite embrace of Cheyenne Mountain, engineers concept but to move with it, to flex and breathe under the most extreme duress. The very skeleton of this subterranean city was a marvel of adaptive engineering. Imagine a building crafted with articulated joints, a sophisticated skeletal system allowing it to stretch and bend by several inches without a single structural failure, even as the Earth itself convulsed during a catastrophic shock event. This was not a static bunker. It was a living, breathing entity designed to absorb the planet's violent tremors. Yet, the true triumph lay in the unseen arteries and veins of this complex. The plumbing and electrical systems, often an afterthought in less critical designs, were here elevated to an art form. They had to survive being violently yanked sideways, twisted and stretched without rupturing, without failing for even a moment. This silent ballet of flexible conduits and resilient connections, though rarely celebrated, formed the absolute bedrock of the entire operational system. And then, the final seal. The blast doors, monolithic sentinels guarding the complex, added another layer of engineering audacity. The main entrance tunnels were not merely protected, they were fortified by two colossal steel barriers. Each door, by some accounts, measured approximately 3 feet thick and weighed a staggering 25 tons. Their purpose was dual: to absorb the direct overpressure of an apocalyptic blast, yet still glide open effortlessly enough to permit the daily ebb and flow of personnel and vital vehicle traffic. The hinges alone were a testament to meticulous design, engineered to endure the ceaseless grind of routine use alongside the theoretical, cataclysmic stress of a nearby nuclear detonation. A failure here meant more than inconvenience. It meant the unthinkable. The command center staff trapped, sealed within a mountain, their mission rendered impossible, their very survival in question. Beyond the formidable springs and the impenetrable doors, the very essence of this complex was its absolute self-sufficiency. During a prolonged crisis, external support would vanish, leaving only what lay within. Engineers integrated independent power generation systems, robust enough to sustain the entire facility for weeks, entirely divorced from any outside electricity grid. Vast reservoirs of potable water were secured, meticulously filtered and stored. Air filtration systems, cutting edge for their time, were specifically engineered to scrub out even the most insidious radioactive fallout particles, ensuring breathable air in a contaminated world. And within its cavernous depths, enough food and essential supplies were meticulously stockpiled to sustain hundreds of personnel in total isolation for extended periods. Crucially, every single one of these vital life support systems, the generators, the massive water tanks, the intricate air handling units, had to conform to the exact same shock isolation requirements as the buildings themselves. They too were mounted on variations of that ingenious spring and flexible coupling philosophy, ensuring their uninterrupted function even as the mountain around them shuddered. Throughout the mid-1960s, construction crews undertook a task of almost mythical proportions. They were, in essence, simultaneously erecting two distinct yet intimately intertwined projects. An impregnable underground fortress, meticulously carved from solid granite, and within its vast chambers, a floating city of steel buildings suspended with breathtaking precision. The coordination was so exacting, the tolerances so fine, that by the time the very last spring was tightened into place in 1966, the entire multi-story structure possessed the theoretical capability to bounce several inches in any direction, then settle back into its original, perfectly aligned position, without a single pipe cracking, without a single connection failing. It was a symphony of engineering, a testament to human ingenuity pushed to its absolute limits. But this monumental feat of construction was merely the prelude. Building a shock-isolated command center, however impenetrable, however resilient, meant precisely nothing if the human beings and the intricate systems housed within it could not perform their designated duties during the absolute worst crisis imaginable. The true test lay in its operational readiness. Cheyenne Mountain became fully operational in 1966, transforming from a construction site into a living nerve center. Staffed around the clock, 7 days a week, 365 days a year, NORAD personnel maintained an unblinking vigil. Their eyes were glued to radar feeds, their minds processing torrents of satellite data, their senses acutely attuned to the subtle whispers of early warning systems, each signal a potential harbinger of global catastrophe. Every second counted. Every decision mattered. This was the ultimate purpose of the floating city within the mountain: to provide a stable, protected environment where critical judgment could prevail amidst chaos. It was a place designed to ensure that even when the ground beneath them shifted, the minds within could remain steadfast, clear, and ready to respond. The springs, the doors, the self-sustaining systems, all were components of a singular, profound commitment to maintain vigilance, to endure, and to act, even when the world outside threatened to break apart. Deep inside a granite mountain, a fortress was forged. Its purpose? To withstand the unimaginable. Yet, within its steel-lined caverns, daily life unfolded with an unnerving, almost surreal ordinariness. Personnel moved through its vast subterranean complex, traversing corridors of reinforced steel, working in standard office environments, and gathering in cafeterias. All of them, unknowingly perhaps, were standing on a structure engineered to defy a nuclear shockwave. This was the Cheyenne Mountain Complex, and its heart was a meticulously designed spring-mounted isolation system. This ingenious system, a marvel of mid-20th century engineering, was conceived to separate the entire massive structure from the Earth itself. The facility effectively floated, its immense weight resting on hundreds of colossal springs and flexible mounts. This radical design was an insurance policy against the ultimate catastrophe, a silent promise of survival should the world plunge into nuclear conflict. A test of its true resilience mercifully never came. The mountain's isolation system was never subjected to the searing fury of an actual nuclear detonation. Yet the fundamental principles behind its creation resonated far beyond the grim specter of atomic war. The very same base isolation logic, the concept of decoupling a structure from its ground with flexible interfaces, found a profound and peaceful second life. It was adapted brilliantly into earthquake-resistant building designs. Today, across seismically volatile regions of the world, from the bustling cities of California to the sprawling metropolises of Japan, hospitals, vital government buildings, and countless other critical structures stand protected by this Cold War innovation. A solution born of the need to survive nuclear annihilation now safeguards countless lives from the unpredictable wrath of natural disasters. Throughout the intense decades of the Cold War, Cheyenne Mountain served as the unwavering physical heart of America's early warning system. From its secure depths, a vigilant eye tracked every satellite launch, monitored the vast expanse of the globe for any flicker of a missile launch, and meticulously coordinated air defense operations across the entire North American continent. Its primary engineering triumph was not in offense, but in an unprecedented resilience, the ability to remain utterly intact under conditions that no human could ever truly simulate outside of an actual, devastating detonation. As the Cold War slowly receded into history, and as satellite-based warning systems matured into sophisticated global networks, the operational role of Cheyenne Mountain began its gradual, inevitable shift. In the mid to late 2000s, NORAD, the North American Aerospace Defense Command, transitioned its primary day-to-day operations to the nearby Peterson Air Force Base. Cheyenne Mountain, while no longer the sole primary hub, was far from abandoned. It gracefully evolved into a critical backup and alternate command center. The facility was never decommissioned, never allowed to fall silent, isolated design. Renewed concerns surrounding electromagnetic pulse attacks, the silent killers of modern electronics, and the ever-present specter of sophisticated cyber warfare have rekindled intense interest in the mountain's unique capabilities. A facility physically disconnected from ordinary infrastructure, a bastion against the interconnected vulnerabilities of the modern world, offers a singular form of protection against threats its visionary 1960s engineers could never have conceived. The very spring system, the heart of its original purpose, has, over the decades, required periodic inspection and meticulous maintenance. Yet, the fundamental engineering, the audacious vision of its creators, has held up with remarkable integrity. It stands as a powerful testament to the precision calculations performed with the rudimentary computing tools of the 1960s, long before the advent of modern structural modeling software that could double-check or even conceive of such a monumental undertaking. Cheyenne Mountain endures, a striking example of military ingenuity, a silent sentinel that continues to adapt, proving that even the most specialized creations can find enduring purpose across the shifting landscapes of human conflict and innovation. History records moments when humanity faced an impossible paradox. Not the challenge of how to dismantle or destroy, but an unprecedented demand: how to preserve life, how to keep vital systems functioning within the very heart of an event designed for absolute destruction. This was the crucible of the Cold War, where engineers, under unimaginable pressure, were tasked with a radical reversal of their fundamental purpose. Their answer emerged in the form of spring isolation techniques, a revolutionary approach to absorb and dissipate cataclysmic forces. What began as a classified necessity to shield critical installations from man-made seismic shocks quietly transcended its origins. Today, these same principles form the bedrock of modern structural protection. From safeguarding the sprawling data centers that power our digital world to fortifying hospitals in the most active earthquake zones, the legacy of that initial, paradoxical engineering challenge continues to resonate. It is a testament to how the relentless demands of a global standoff inadvertently forged the very methods that now ensure civilian safety across generations.